In this video, we're going to talk about the chi-square test for goodness of fit. Uh, Later, we're going to talk about the chi-square test for independence. So what is the chi-square test? Well, a chi-square test for goodness of fit in any case is a test to determine if a population has a specified theoretical distribution. The test is based on how good a fit we have between the frequency of occurrence of observations and of an observed sample and expected frequencies obtained from the hypothesized distribution. To be more precise, the goodness of fit test says the following. A goodness of fit test between observed and expected frequencies is based on this chi-square test statistic. So chi, this is the Greek letter chi, pronounced chi. The chi-square test is the sum of the differences between the observed values and expected values divided by square divided by the expected values. So the chi-square test statistic is a value of the random variable whose sampling distribution is approximately the chi-square distribution, which I talked about in the previous video. And OI is the observed frequency of the cell, and EI is the expected frequency of cell I. For level of significance alpha, the chi-square test statistic must be greater than chi alpha squared. This will constitute the critical region for which we will reject the null hypothesis. The decision described, so you should have at least 5 frequencies observed. And the number of degrees of freedom for the chi-square test statistic is given by the number of cells after combination minus 1 minus the number of parameters estimated by calculating the expected frequencies. So in our examples, we won't use the yellow part of this formula, just the green part. Okay. So number of degrees of freedom. We just use this green part basically. Let's do an example. Uh, so consider the tossing a coin. Okay. I mean a die. Sorry. And we observe the following times it falls 1, 2, 3, 4, 5, and 6. So in total, in fact, tossed it 120 times. To 5% level significance, determine whether this is a fair or not fair dice. This is so our null hypothesis in this case is the dice we threw is a fair dice, and the alternative hypothesis here is that it's not a fair dice. So since we have a 5% level significance, our chi alpha nu is so alpha is 0.05. Our nu is the degrees of freedom. Remember, it's the number of cells, so 1, 2, 1, 2, 3, 4, 5, 6. So 6 minus 1, number of cells minus 1. It's 5. So it's 5 degrees of freedom. So let's look at our chi-square distribution table. Let's clean it up a bit. So we're looking for 0.05 and 5 degrees of freedom. So we'll go here. So it's 11.070. Okay, 11.070. 11.070. Okay. So now let's calculate our chi-square test statistic. which remember is the sum of observed values, sum of the minus the expected values divided by expected values. So these are the observed values, which we label O sub I. The expected values, E sub I, well, since we tossed the coin 120 times, then we should expect that the probability of landing either 1, 2, 3, 4, 5, or 6 is the same. So we just divide by 6 to calculate the expected value. So expected value is when you toss a die 120 times to land 1 is 20. Here's also 20, here's also 20, land 4, 20, 20, 20. And let's calculate, for example, the difference. Okay. So the OI minus EI, 0, 2, 17, oh sorry, 3 minus 3 minus 2, here is minus 1, OI minus 4. So basically you're summing all these. So 0 squared plus 2 squared plus minus 3 squared plus minus 2 squared plus minus 1 squared plus 4 squared divided by E sub I. So all the E sub i's are the same, which is 20. So in fact you get, so this is 4 plus 9. Okay, you don't need to do the arithmetic. In fact, this would be 1.7. Okay, so pictorially, what's going on is, so the region where, so this is chi of u, this is 11.070. This is if the test statistic falls inside this region, then we reject H naught. But look, our chi-square test statistic is right here, 1.7. So it falls outside the critical region. So therefore, since chi-square test statistic is less than chi alpha nu, then we accept the null hypothesis. And we have a fair die. The die we toss is a fair dice. Okay. So now let's try our second example. Researchers conducted a survey of 1,600 coffee drinkers, asking how much coffee they drink in order to confirm previous studies. Previous studies indicated that 72% of Americans drink coffee. The results of the previous studies on the left, so this is the previous historical data, and the survey on the right are the present data. At 0.005 significance, is there enough evidence to conclude that the distributions are the same? Well, so in this case, our two hypotheses are null is the two distributions are same, and our alternate hypothesis is they're different distributions. Since alpha is equal to 0.05, then critical region can be determined by, so the degrees of freedom here is the number of cells, so 1, 2, 3, 4, so it's 4 minus 1, so it's actually 3. So let's look at chi-square distribution with 3 degrees of freedom. 3 degrees of freedom is right here, and then we intersect with 0.05 again, so 7.815. Okay, 7.815. 7.815. Okay, so let's highlight that for later use. So now how do we calculate? This is going to be the observed values. What are the expected values? Well, for 1600 coffee drinker sample, then the expected value must be 0.15 times 1600, which is going to be 200 and what's it going to be? 240. So this is obtained from 0.15 times 1600. Similarly, we multiply 0.13 times 1600. We obtain 208 here. Then we have 27% times 1600 is 432, and here will be 739. Okay. So we can calculate the chi-square test statistic here. So remember, it's the sum over the observed values and expected value square over. Yeah. So explicitly, it's going to be 206 minus 240 squared over 240 plus 193 minus 208 squared divided by 208 plus 462 minus 432 squared divided by 432, and then finally we have 739 minus, whoops, this must be 720, sorry, 720 squared divided by 720. When you plug that into your calculator, you actually get 8.483. And now let's compare these two values. I mean, clearly, so this is greater than chi alpha nu squared. So that means that it falls in the test statistic falls in the critical region where we reject the null hypothesis. So we reject the null. And in fact, there is a difference in distributions of coffee drinkers in the current survey. Different distributions. See? Then let's just do maybe one more example. The department store called A has 4 competitors called B, C, D, and E. Store A hires a consultant to determine if the percentage of shoppers who prefer each of the 5 stores is the same. A survey of 1,100 randomly selected shoppers was conducted, and the results about one of the stores prefer are below. Which is there enough evidence using significance level 0.0005 to conclude that the proportions are really the same? That is, do the customers really like the stores the same? Okay, so here our null hypothesis is customers like stores equally. And then our alternative hypothesis is customers like stores unequally. Here our chi critical region is determined by kappa mu. Chi is 0.05. Our degrees of freedom is how many cells? 1, 2, 3, 4, 5. 5 cells. So it's 5 minus 1, so it's 4. Let's get a chi-square table at 4 degrees of freedom. Okay, we use green this time. It's 9.488. 9.488. 9.488. So this is the observed values. the expected EI plus 1,100 randomly selected shoppers. So divided by 5 sales. So expected is 220. Maybe because we expect the customers to like the stores equally. So then again we figure out the test statistic. Okay, I'm not gonna write out explicitly again. But in fact, once you calculate this out, it's going to be 14.618. And so you compare this and this. Clearly, the test statistic falls inside the critical region, right? So therefore, this is greater than chi alpha nu squared. So therefore, we reject the null hypothesis. Reject. And customers like stores differently. Right? Different. Not the same, okay? And the last one, maybe you can do this one at home, okay? Do at